Are we all set?
We're on.
Okay, great. Okay, it's a pleasure to have here today Dr. Anthony Yezzi from Georgia Tech. He's from the Electrical Engineering Department. Dr. Yezzi graduated from University of Minnesota and subsequently went and worked as a researcher at MIT and then joined the Department of Electrical and Computer Engineering, or the school, I should say, of Electrical and Computer Engineering at Georgia Tech. And he's been doing a lot of work on variational methods and nonlinear filtering, nonlinear PDE, and in imaging and computer vision. It's a pleasure to have you. Thank you for coming.
Thanks. Okay, so we can be casual since there's just a few guys here, so so there's no need to be overly formal. What I'm going to be presenting is some work that I did in conjunction with my student Ganesh, who's going to be graduating in a couple of years here, and a colleague of mine, Andrea Minucci, from La Scuola Normale in Pisa. And so as you can see, the title of this is called Sobolev Active Contours, and we'll explain how we came up with that name halfway through the talk. So I'm going to start with just some introductory remarks about the role of shape in computer vision, and basically there's two types of categories. One is shape optimization, where the goal is to actually find a shape. And then the other is shape analysis, which is given a shape, you want to do some analysis on it, measure some properties. And a remarkable thing about these two areas in computer vision is that for the last 20 years, in this category of shape analysis, oh shoot, all right, hold on. In this category of shape analysis, lots of people have devised metrics for comparing shapes, measuring the distances between curves, how do you take the average of curves. There's even been work in the last few years on doing principal component analysis of shapes. But there's no consistency in the method used for measuring distances between curves. Everybody chooses their favorite metric, and some of them aren't even real metrics. Yet, if you look at the shape optimization literature, where people are doing active contours and gradient flows, whether they're contours or surfaces, parametric or level sets, there's been a remarkable consistency in the assumption of an underlying metric on the space of curves that's used in order to define a gradient. So most people don't even pay attention to this. I'll get to a slide in which we show the procedure most people follow. Most people are completely not paying attention to the fact that when they write down a gradient flow of a certain energy, they're assuming a certain metric structure on the underlying space. And the remarkable property is that in 20 years of active contour literature, everybody's completely consistent about this, whether they know it or not. This complete consistency, which is in contrast to the shape analysis community where everybody uses their favorite metric. So we can ask ourselves, can we take this very consistent choice of assumed metric structure that people have used in shape optimization and do shape analysis with it and derive metrics for curves? And I'll talk a little bit about that. And then the next question is whether or not we can make a nice metric out of this, the one that's already used. Can we pick a different metric that maybe has better properties than what's being assumed here, and then redo shape optimization with respect to a different metric? And that's where we'll get to Sobolev active contours. So that's the outline of the talk. So first, I'll just set up some notation. We're going to be considering closed curves, C, in the plane. Most of what I'm going to say occurs through perfectly well for space curves, but we're going to just assume plane curves for now. And then we're going to consider the manifold M of all possible closed curves. And we're going to assume that these curves are smooth. I'm not being very precise about what degree of smoothness, but just assume that M is the manifold of closed smooth curves. Right? So any two curves, C0 and C1, are thought of as points on this manifold. Oh, did I? Oh. So any two curves are thought of as points on this manifold. And then we can also think of an abstract sense of a trajectory gamma on this manifold. Oh, then it won't flip?
No, the pen you can write with.
Okay.
There you go.
Okay. All right, so then we can also consider trajectories. Well, imagine that started, I see. see if I can repair it. All right. You can consider a type of trajectory on this manifold that connects two curves. And this trajectory is a homotopy. It's a morph from one curve to the other. So it's a curve of curves. Right? So the question is how do you define lengths of trajectories in this manifold? So if you give me a morph from one curve to the other, can I define a length of that morph? Okay, and of course the answer is yes, but it depends on what metric structure you put in this manifold, and we're going to talk about that.
Anthony, could you put your cell phone on the desk? It might be interfering with the wireless microphone.
Sure. Is that better?
We'll see. Thank you.
Okay. Okay, so now let's move on.
Why don't you erase just in case?
Now it's not moving. Oh, do I have to erase before I can move on?
I don't know. So
Try
to close the.
What if I close this thing? Okay, now I'm stuck.
Pull the pen back.
You need to hit your mouse button because you're still on a pen, it looks like.
That was the mouse button that I just hit.
Put the pen back.
Maybe escape.
Yeah, if you put the pen down.
Okay. We're never going to get through this talk. All right. So I assume a lot of you are familiar with active contours. And if you look in the shape optimization... What? Okay. If you look in the shape optimization literature, especially early on, there were two classes of active... So first of all, there's an active contour, of course, is any curve that you put in the image that evolves according to forces that come from the image. But there's one big class of active contours, and those are the active contours that come from variational methods, right? So the forces that are derived to move the contour come from taking the gradient of some energy that I'm trying to minimize. So we're going to be exclusively talking about this class of active contours. So early on, most of the energies that were proposed to be minimized by the active contour were boundary or edge-based energies. I integrate around the curve some function with respect to arc length. And then, of course, this function is supposed to be a feature detector of some sort. Usually it's chosen to be small near an edge, but it can be chosen to be small near any feature where you want the contour to stop, and then you evolve the contour to minimize this. Then there's the class of region-based energies where instead of taking the energy of integrating some feature just over the curve, I look at all the area inside the curve and I integrate some feature. And I look at all the area outside the curve and I integrate some feature. Or maybe compute some statistics. Okay. But I don't need to explain that these have a lot of applications in segmentation, tracking. We're going to skip that. What I'm more interested in now is in this procedure. So how does the general procedure work? Whether you're using edge-based or region-based or even more complicated hybrid energies, the generic procedure is you choose an appropriate energy function. Well, usually you want the energy to be geometric so it doesn't depend on how you parameterize the curve. And now, how do you arrive at the final evolution? Well, the first step is after you choose the energy, you compute the directional derivative. So h is a direction that I can move in the space of curves, and that corresponds to one possible way to perturb the curve. So I can represent that as a vector field on the curve that tells me where each point on the curve is wanting to move. So that entire vector field on the curve is a direction h. And then now I look, if I perturb the curve in a small amount in this direction h, I can look at how much the energy changes. Okay, so you compute this directional derivative, and then you do some work. You do some integration by parts. You do some calculus. And you get the expression to look like the following. It looks like the integral around the curve with respect to arc length of the perturbation dotted with something else. Now that something else is going to depend on what the energy is. So you're going to work to make sure you isolate the perturbation over here. So up here I call the perturbation h, but in general you can think of the perturbation as dc dt, the way the curve's evolving. So here I'm calling it ct. So whatever you do by your integration by parts, by your calculus to get to this form, will give you something over here that's a function of the energy that you chose. Now this thing that you get over here, what I'm calling v, what's the next step? The next step is you call this the gradient. So this is what's done in the literature. Now, there's a huge leap that goes from 3 to 4. That if you want to call this thing the gradient, then there must be something special about this form of the directional derivative that allows you to call that. And the thing that has to be special about this form is this has to take the form of a certain inner product structure that you're assuming on the space of all perturbations of your curve. And we're going to talk about that in just a minute. Okay, but just for now, most people in the literature just kind of do this on blind faith. They go from 3 to 4, and they don't really talk about what the assumptions were about the inner product assumed in this formulation of the directional derivative. So once they get the gradient, then of course step 5 is very natural, and that is pick some initial position of the curve, and now always move in minus the gradient until you reach a steady state. Okay, so I want to focus now on 3 to 4. So keep in mind that the form of this, it's the integral over the curve with respect to arc length, that's very important, of the product of your perturbation with something else. Now, of course, this something else is also a perturbation, but it's the magic one. It's the gradient perturbation. So keep that structure in mind as we continue. So let's just work through one example of this procedure and see how it works. So let's just take the geodesic active contour model, right? So that's the first one I showed you. The energy is the integral of some function phi with respect to arc length over the curve. And again, the typical thing is you choose phi to be 1 over 1 plus the gradient, so it's small near an edge. Okay, but that's not important. The main thing is the calculus we're getting ready to do now. So now you calculate the directional derivative. So what do? You assume that c varies in time. And you take the derivative in time over your family of curves. And of course, now your energy varies in time too, so you take the derivative. And after some work, you can manipulate it so it looks like dc dt, the perturbation that you're trying to determine, dotted with something else, integrated over the curve with respect to arc length. Okay? So now we do this magic step. So now that we have it in this form, we take everything here that's not dc dt. Everything that's here is dependent on the fact that I chose this energy. And I'm calling this the gradient. Now, of course, I have a minus sign, so when I take minus the gradient, I don't have to worry about it. I just drop it. So I call that this is the gradient, and now I say my gradient flow is dc dt is minus this, and that's what I get. And of course, this is the standard geodesic active contour flow. All right. So what's the assumption? So the assumption is that you jump from computing the directional derivative of your energy and manipulated it into this form where it's the integral of, over the curve with respect to arc length of your perturbation with something else. The jump that says that this something else is the gradient makes the following assumption. We're assuming that this integral describes an inner product. Okay, so first I have to tell you what is the space over which we're taking the inner product. The space is the space of all vector fields on the curve. So a perturbation of the curve I can describe as a vector field, which at each point in the curve tells me which way and with which velocity I'm going to move, right? So that's your space, all possible vector fields. What is the inner product now? The inner product is that if you give me two such vectors perturbations, so dc dt is a possible perturbation of the curve. The gradient is the magic one that I want, the optimal one. So here's two vector fields on the curve. I take the inner product, and I'm assuming that that inner product is exactly expressed by this integral. It's the integral of the Euclidean dot product pointwise integrated over the curve with respect to arc length. So I'm calling this now an inner product. From now on, I'm going to call this inner product H0. It looks like an L2 inner product. The biggest thing that makes it special compared to the standard L2 you might see in a functional analysis text is there's a very special measure. Okay, the measure has to be arc length. Okay, it can't just be some arbitrary parameter of the curve. It's arc length. So I'm going to call this H0 from now on, this inner product. And this is a standard one. So this technically now, I showed in the special case of dc dt and the gradients. If you just give me any two vector fields, H1 and H2, on the curve, I'm going to call the H0 inner product just the integral over the curve with respect to arc length of the standard Euclidean dot product pointwise, and then I integrate. Okay? So this is what's assumed now. This inner product structure is assumed in every single variational active contour method that I've ever seen in the literature for 20 years. Most people don't draw attention to this, and some people might not even know it, but this is what's assumed. So what's an example now? So we already saw the example of the geodesic active contour. Let's take something just purely geometric. Forget segmentation, just a purely geometric flow that's very well studied. It's the geometric heat flow, where I evolve a curve in the normal direction with respect to curvature, the mean curvature flow. So this arises as the gradient descent for arc length. So this is the way you shrink the length of a curve in an optimal way. All right. It has been called the gradient descent for arc length for many years. But it's only the gradient descent for arc length if you're using this H0 inner product. Okay, so implicit in the definition of gradient is the assumption of what inner product structure you're assuming in your vector space. If you change the inner product, this is no longer the gradient descent for length. It will still decrease length. It will always decrease length. But the question is, what makes it the gradient for length is the choice of the H0 inner product that we just saw on the previous slide. Okay, so based on that inner product, then yes, the geometric heat flow is in fact the gradient descent for arc length, but only with respect to that inner product. Okay, so this has a lot of nice properties. I'm not going to dwell on these. Okay, so now let's go to shape analysis. So what are the problems in shape analysis? Well, the most fundamental problem in shape analysis is how do I measure the distance between two curves? Okay, now from that you can build up other things. Once you know how to do that, you can compute averages of curves. You can do principal component analysis. You can develop, probabilistic models, distributions. Okay, but the fundamental problem boils down to how do I compute the distance between two curves? Look at the literature and you will find dozens, at least dozens of proposals for this. So two that are talked about a lot, just because they're easy to define, are the symmetric Hausdorff distance, where I take between two curves, a point on one curve, I find the closest point on the other curve. And then I do that for all the points in the original curves, and I take the soup. And then I add to it the problem in reverse. The other is a set symmetric difference, which is a little bit different. I think of the curves as this only works for closed curves that have an interior and an exterior. And I look at the set bounded by the curve, and I take two curves and I overlap them, and I look at how much of the set belongs to both curves together. So I look at basically the intersection, and then I subtract the intersection from the union to look at how much stuff is in one curve but not in the other. And then I call that the set symmetric difference. So these are two simple ones, but there's really been a ton of other distances proposed in the literature. This is just two of them. Now, once you have this, now there's also the question of how do I compute the averages between shapes? Okay, well, if I'm representing the shape parametrically, it's easy, right? As long as the parameter space of the two shapes is the same, I just take the corresponding points in the two shapes and I average them point-wise, and then I get an average shape. So it's straightforward. It's just the arithmetic mean. Now, you can do this also with implicit representations. If I have sign distance functions, for example, of my shapes, and I can add two together and I can take the average, it won't be a sign distance function anymore, but I can still treat it as an implicit representation of a shape and take the zero level set. Okay? So the problem is that both of these techniques, this one depends on how I parameterize the curve. I will get a different answer for the mean. And the different answer is not just a reparameterization of the first. It will be a totally different shape. The same thing happens down here. When I do the implicit representations, if I use two sign distance functions and take the average, I'll get one zero level set. If I choose a different canonical way of embedding the shape implicitly and I average them, I will get a different zero level set. So both of these depend on how I represent the shape, and as a result, they're not intrinsic methods of finding a mean. So a more intrinsic thing that is, if you give me a method to compare distances between shapes, you just do the classical thing. So you choose the mean C bar to be the argmin of the sum of the squared distances between itself and every other shape in your set. Okay, and that thing that minimizes the sum of the squared distances is the mean. So in a linear space, this coincides with the arithmetic mean, okay, but only in a linear space. The problem is that shape is very nonlinear, and that's why you don't have this simple thing. So I'm not going to dwell on this. You guys know that if I can do means, then the next thing I do is pre-CA. I can do principal component analysis. I can do probability models. I'm going to skip this stuff because I want to get to the more interesting part. Okay, so now let's get back to this inner product structure. When you have an inner product on a space, of course you have a norm, right? You can think of the norm as the square root of the inner product of a vector with itself. Once I have a norm on a space, I have distances, right? I can compute lengths of trajectories between one point and another. So I take the trajectory, I take the derivative along the trajectory, that gives me a vector. I take the norm of that vector, and I integrate the norm of that vector along the trajectory. So that's the distance. That's the length of a trajectory. Now, distances is just given by the argmin of the lengths of all possible trajectories to 2 points. So once I have an inner product, everything else follows naturally. I don't have to invent anything or be heuristic. Everything comes from that. So now the question is, these types of metrics are called Riemannian metrics. Now, what are the Riemannian metrics that have been considered on the space of curves? So the simplest one, which is the one that is assumed in the shape optimization literature very consistently, is this one that I called H0, which is you give me two. So what are the vectors, again, that I'm considering are vector fields on the curve. So you give me two vector fields, and the inner product is given by integrating with respect to arc length the dot product. Okay? Now, there's another one that was proposed by Meeker and Mumford, which is one term that looks like this. So I have 1 times this same dot product over here. And then but instead I add to it some positive weight A. A is some positive number greater than 0 times the curvature squared. So I'm going to put more emphasis on the places of the curve where the curvature is high. Whereas here I don't care what the curvature is. I just take the perturbation and I sum it up over the curve. Here I'm going to weight the sum so that the curvature can when it's low, I don't care. When it's high, I care more. So then there was another one that this is what was proposed.
Why do you call it HA? I mean, Sobolev spaces are typically...
This is not Sobolev.
Then
they called it HA. This has nothing to do with Sobolev spaces. This is their convention. They were just using the notation.
Okay.
Yeah, I agree. But that's the notation. Well, probably when they originally proposed this, they weren't thinking of Sobolev spaces, right? So they were just thinking of this here. So H0 and HA, because if I substitute A is equal to 0, I get this. So that's probably why they use.
Well, I mean, you do have the curvature. The curvature is proportional to the second order derivative.
Yeah.
So in a sense, you are defining a Sobolev norm.
No, because we're looking. So the curvature is the derivative of the curve, where the Sobolev norm would be the derivative of H, the vector field on the curve, which has nothing to do with the curvature.
We can talk about it later. Okay.
Yeah. Anyways, there's nothing Sobolev about this. Okay, so it's just that they're weighting this by 1 plus some alpha times the curvature, and in the special case where not alpha, in the special case where A is 0, you get this, and so that's probably why they called it HA, because you plug in 0 for A and you get H0. But don't interpret A as any kind of Sobolev norm. It's not. Okay, it's still a 0 order. If you want to think of it as Sobolev, it's still a 0 order Sobolev inner product, but it's a weighted one. Okay. Okay. Now then, what we proposed instead, this is some work that I did together with my colleague Andrea Minucci. They proposed this. There's some pathologies with this, and I'm going to explain the pathologies about this in a minute. So to fix the pathologies, they introduced this curvature. What we did was we just took a factor outside of the inner product that depended on the curve. And so we assumed that the factor is positive. And when you do something like this, it's called a conformal factor, right? Because now the inner product is the old inner product times some conformal factor. Whereas here you have something introduced inside of the integral. You cannot write their inner product as the H0 inner product times something, because the thing is actually inside the integral. So we propose this conformal inner product to replace this. And so now in the special case that you choose phi is equal to 1, you get back the H0. So these are two different generalizations of H0. This was the one by Meeker and Mumford. This was the one that I proposed with Andrea Minucci. Now, this is what I'm the most interested in this talk, is you can consider Sobolev type inner products. So here, in addition to having this term up here where I take my vector fields H1 and H2 and multiply them and integrate, I can then also do the same trick with the derivatives of H1 and H2. Okay, now these aren't derivatives of the curve. These are derivatives along the curve of whatever the perturbation is. So the curve can be straight or curved, it doesn't really matter. So I add to this term now, I take the derivatives of h1 and h2, I take the derivatives in arc length, and I sum them up. And in addition, I'm multiplying these derivatives, these derivative inner product terms, I multiply them by the length to a certain power. And the only reason I'm multiplying these by length to a certain power is so that if I rescale the curve, both of these terms scale in the same way. So I want my inner product to scale naturally with rescaling of the curve. Otherwise, what happens is because these are derivatives with respect to arc length, if I multiply the whole curve by lambdas, let's say, then this one will scale by lambda, but this one will scale by lambda cubed, right? So, by lambda divided by lambda squared. So I'm going to compensate for that, I need to multiply by the length. So so this is just a technicality. It's not really crucial to understand intuitively what's going on. So the main thing is that I have a zero order term which is the same, plus higher order terms where I take where I apply this exact same inner product, but I substitute these by the derivatives. Okay, so these are the Sobolev type metrics.
How is the derivative of h related to the curve? I'm sorry, you lost me there.
The only role that the curve plays is to tell you what the arc length parameter is. Okay, h is a vector field on the curve, not the curve itself. So these are inner products applied to vector fields on the curve that represent how I'm going to change the curve. It doesn't matter what the curve itself is.
Okay.
Okay, so I have...
So they're independent of the curve.
Yeah. So I have a curve. And then now I'm going to evolve the curve, and I want to pay, I want to associate a cost to perturbing the curve, which has nothing to do with the energy I'm minimizing. Okay, of course, as I perturb the curve, I'm changing the energy, but that's a separate thing. Just on its own merits, what is the cost of moving the curve a little bit? So that depends on these inner products. So motion of the curve can be described as some vector field on the curve.
Right.
Right, so I have this vector field, and it's just telling me how different points in the curve are moving.
Yeah.
Right? And so this is what I'm calling h.
Okay.
Okay. Now I need to parameterize it somehow. That's the only way the curve plays a role. So I'm going to parameterize this as a function of the arc length of the curve.
Okay.
But I don't care what the curvature of the curve is. If I want, I can straighten out the whole curve as long as I keep the arc length and look at the vector field h, and that's a valid way of looking at it too. Okay. So h is just a set of motion vectors on the curve.
All right.
Okay. The only role of the curve is that when I'm taking derivatives of h, I'm going to take the derivatives with respect to the arc length parameterization of h. Okay. Other than that, I don't care what the curvature is, nothing. I don't care what the length is. Okay. All right, so I guess I have to put this down. And now, did it move?
No. Okay. Now you move.
Okay. So now, so let's recall now the problem of having two curves representing 2 points on a manifold and then looking at paths between the two curves. So the paths, so here's my initial curve C0, here's my final curve C1. Now a trajectory connecting those two curves will look like a family of curves, a homotopy. So now I have to parameterize this thing. So you could just pick an arbitrary parameter u that goes around each curve and an arbitrary parameter v that goes along the trajectory. And you can say both go from 0 to 1, and that allows you to make correspondences, compute derivatives in a natural way. The problem is these parameters are completely arbitrary. So you want to come up with geometrically meaningful ways to parameterize this homotopy. So we already know what to do. So there's two parameters. One parameter goes around each curve, and one parameter goes from curve to curve. So we already know what to do with the parameter that goes around each curve. The geometrically meaningful thing is to use the arc length parameter. Okay. Now, what about this parameter v? Does the v parameter depend on how I parameterize each individual curve? The answer is yes, because how I parameterize each individual curve defines what I mean by taking the derivative in v. Because when I take the derivative in v, it means that I'm holding u constant. So it assumes a certain correspondence from one curve to the next in order to tell me what it means to move in the v direction. So even v depends on how I parameterize the curve. So I need to fix u by switching to arc length, and I need to fix v somehow so it doesn't not matter how I choose the correspondences between the curves. So we already know how to fix u. We divide by the speed to make it into arc length. The way that I fix v is I'm going to define a new operator, v star. So I can, from v, I can make a differential operator, ddv, which is measuring directional derivatives in this direction. I'm going to make a new directional derivative operator, which is ddv star. And what it is it's ddv, so I'm going to go in some direction v, which assumes a correspondence from the point that I'm starting from to the point that I'm going to. But then I'm going to subtract any contribution that causes me to move tangentially along the curve. Okay, so if I associate 2 points on neighboring curves infinitesimally, close to each other, and that direction that I move has a tangential component on the curve, what it means is I'm wasting energy, right? I want the most efficient, what I want v star to mean is that if I do dv star, it means that I'm moving in the most efficient way from one curve to the next curve on this homotopy. And if I move in a direction that causes me to translate a little bit along one curve, that means there was a more efficient way to go to the next curve. So this is only the part of ddv that's orthogonal to the tangent. That's what I mean by ddv star. So s is arc length along the curve. V star you can interpret as the direction that you go along the homotopy that's as direct as possible. Okay, now in terms of those two differential operators, we can write down some equations that have now these are geometric operators now because they don't depend on how the curves are parameterized. Now we can meaningfully describe a few things about this inner product. So let's recall that in the H0 inner product, so I said in the beginning that once you have an inner product, you can step by step build up a distance between two curves. So let's recall the procedure. So the first thing you do is, given two curves C0 and C1, you consider an arbitrary trajectory between the two curves. Okay, so that thing that I showed you, that thing parameterized by V star and S. Now I take the derivative along the trajectory. So along the trajectory in the geometric means I take the derivative in this V star operator. And then I take the norm of that. Now I have to pick the norm because this is an infinite dimensional vector. So I'm going to use the H0 norm, which was the one associated with that inner product that we've been talking about. And then now I take the integral of that. And that gives me the energy. And then now if I take the square root of this, then I get the length. Okay, but minimizing the energy and minimizing the length is the same thing. So just to avoid the square roots, I'm just going to ignore it. So this is instead of the length now of the homotopy, it's just the energy of the homotopy, just because I'm leaving the square. The point is that it depends on the norm that I use for the derivative of the curve along the homotopy, because that's a vector field, and I need to associate a norm to that. So if I use the H0 one, that means that it's a double integral. The outside integral is the integral in this space, and then the inside integral is defining this norm. So it's the integral over the curve with respect to arc length of CV star dotted with itself. That's what you have to use if you use the same inner product that's been assumed in the shape optimization literature. So now when you have that energy, you can do calculus of variations, and you can derive an Euler-Lagrange equation, which is a necessary condition for a trajectory from C0 to C1 being optimal in that metric. This is the Euler-Lagrange equation. So the nice thing is that because we're using these geometric parameters S and V star, it looks really beautiful. I mean, we can really understand what this thing is saying. So this is saying that the second derivative along the homotopy minus the second derivative along the curve, that's just the curvature, weighted by the speed that we're going along the homotopy, that has to be equal to 0. Of course, there's the half. Here's the problem. Notice that the signs, these are both second order terms, second derivatives of the homotopy. One is a second derivative along the curve, one is a second derivative along the homotopy. Notice that the signs are opposite. Now this is a problem because unless I start off with a homotopy that just magically satisfies this, now the odds of that are pretty low. I mean, what you'd like to do is start off with a homotopy that might not be the best choice and flow along the descent of this energy. So the problem is because the Euler-Lagrange equation has two second order terms with opposite signs, no matter what direction you flow, you're going to have one forward diffusion and one backward diffusion. See? Now, if these are both negatives and then I take and I flow along negative of this, then I can 2-4 diffusions, that's perfectly stable. If they're both positives, then I could just flow along this, and that's 2-4 diffusions. But they're opposite signs. So when I compute the gradient to descent, this minimizing flow, I get a forward diffusion and a backward diffusion. The backward diffusion is ill-posed. So this is a very surprising result. And it implies that there's something weird about this metric. Because this is the most basic problem that you can solve in a metric, is finding a minimizing flow of trajectories with respect to that metric. And the fact that the most basic problem that you would want to look at from a variational perspective associated with this metric leads to something horribly opposed suggests maybe there's something weird about this metric. So here's the weirdness. Suppose that you have two curves that are just unit intervals. One's going to be on the y-axis. Wow. Okay, one's going to be on the x-axis, and one's going to be on the y is equal to 1. So they're just shifted by 1. Now you would hope that the optimal way, according to any reasonable metric, you would hope that the optimal way to move from this curve to this curve would just be to do a parallel translation. And you can compute what the energy is. In that HCO inner product, the energy of going from here to here, assuming that the length of this is 1 and the distance of this is 1, the energy is 1. Okay, so it's an easy, you just compute that double integral, you'll see. Suppose instead you propose kind of a weird way of going from the bottom curve to the top curve. Pick an interval that fits an even number of times between 0 and 1, so 1 over some integer. And now over that interval, start growing a triangle. And keep the base of the triangle fixed. And then keep moving up until the tips of the triangle hit the opposite curve. Now that's half of the homotopy. The next half is going to reverse this. You're going to fix these points up here, and you're going to retract the tips that were on the bottom. Okay? So you went from this curve to this curve. Now your intermediate curves look nothing like this, but this is certainly a valid path to go from this curve to this curve. Now, let's consider a family of such homotopies indexed by k, where k tells how many intervals I squeeze in to this unit interval. So as k goes to infinity, I get these really, really narrow spikes. If you compute what the energy of the homotopy is as k goes to infinity, the limit is 0. Which is telling you that for arbitrarily small cost, you pick any tiny cost you want, any epsilon, and it shows that I can find a rather bizarre way to go from this curve to this curve that costs less than your epsilon. So now if you do the standard thing that's done in Riemannian geometry, that once you know how to compute lengths of trajectories between 2 points on a manifold, that you define the distance between those 2 points as the infimum of the length of all possible trajectories, well, according to that definition, the distance between these two curves is 0. And they're not the same curve. Now, this is a special case, but you can prove that this same phenomenon can occur between any two curves. All right, so I showed something that you can calculate. If you're surprised by this and you want to do the calculation, it's a tractable calculation. So you can show that the limit's 0. In the generic case, it's not easy to calculate, but you can prove it. So this is the weirdness that we were hinted existed when we looked at the flow induced by the Euler-Lagrange equation of this metric. So this tells us why. We got this really weird backwards heat flow. If you think about it, what does a backwards heat flow want to do? Well, if there's a little bit of curvature somewhere, it reinforces it. And as the curvature gets bigger, it reinforces it really faster. It exactly shoots out spikes. And what this said was the best way to go from here to here is by spikes. So it's actually completely consistent. All right. So the question is, can we fix this metric? So the infimum is 0. That's bad. Let me show you another pathology with this metric. All right, consider again the case where my two curves are the unit interval on the x-axis and then shifted up by 1. Now I showed you a really weird homotopy, which was these families of spikes. Now instead, you pick one for me. Pick any homotopy in the world just with one constraint, that see, all these intermediate curves are arbitrary. You picked them. The only constraint that I'm going to ask you is that the endpoints of these two curves agree. So if I look at the height at the endpoints, whatever I start with here, I end up with over here. Okay, because now why do I want that? Because what I'm going to do now is from your homotopy, I'm going to build a sequence of homotopies. So your homotopy will be the first one in the sequence. Now the second one in the sequence I'll obtain by splitting this in half, and I'm going to compress your homotopy. So since it started and ended at the same point, then that means I can continue here and repeat it. Okay? Now in addition to squashing it in this direction, because it starts off flat and ends flat here, that means I can cut it in half vertically, and I can scale it in this direction too, and then repeat it here. So basically, the second homotopy in the sequence is going to take this homotopy scaled both this way and this way, and I'm going to have it 4 times in 4 different quadrants. Okay, so everybody gets what I'm doing? Now, of course, this would represent the 4th one in the sequence. Now I divide it into 4 by 4, and I scale it by 4 here, I scale it by 4 here. So I make kind of a tessellation of the unit square. Okay, now I can go off to infinity. So now I have a sequence of homotopies. If you take the energy induced by the H0 inner product for this homotopy, it's, of course, a function of what homotopy you picked. But here's the weird thing. Whatever that energy was, it's the same for any one of these other homotopies. So you can see that there's no derivatives involved. The way you scale it, you'll see that the energy for all of these other homotopies in the sequence is identical to your initial one. However, this homotopy, you can see it. Okay, you can prove it, but you can see it right away. This homotopy, as I go to infinity in my sequence, and I make these smaller and smaller, it's converging to this homotopy, right? Because as I'm squashing this down in this direction, pretty soon, okay, imagine that I split this like this. All of these homotopies in here eventually are flattening out. So every time I divide in the vertical direction more, the amount of fluctuation first it gets chopped in half, then it gets chopped in third, then in fourth, then in fifth, then in sixth. So it's flattening out. And then, of course, when I'm repeating it this way, if it's flat here, it stays flat all the way around. So this is converging uniformly to this homotopy. Now, the energy of this homotopy is 1. Whereas the energy of this homotopy and all the other ones was whatever the energy of this one you picked was. So what this tells you is that in this metric, even the energy of a path, let's even forget the length of a path, right? I mean, with the square root. Just the energy of a path is not a continuous function. Oh yeah, I have to put this back. Now what? Okay. So what do people do in analysis when you don't have continuity? In particular, when you're trying to minimize things, what you really care about is lower semi-continuity. But in this case, let's just think of continuity. You can try to think of the relaxation of your energy. So the limit, so the problem is it's not continuous. So if I take a sequence that converges to a point, the limit of that sequence will not necessarily be the value at the limiting point of that sequence. That's because it's not continuous. So what you could do is change your definition of the energy and then take all possible sequences converging to a point, take their limits, and then take the infimum of all of them. That's called the lower semi-continuity relaxed. Now, what you saw in the first slide shows you that I can always come up with a sequence from one curve to another that costs 0. So what this says is that the lower semi-continuity relaxed of this energy is 0. So the only metric you can build out of this, no matter what tricks you play in analysis, is a trivial metric that says the distance between any two curves is 0, which is completely useless for shape analysis. Now, I'm going to skip this because I want to get to the active contour part. But some proposed fixed have been introduced to try to fix the problem with H0. What I'm going to do now is skip to saying, instead of trying to repair H0, let's just say it's a bad metric. Why did we spend so much attention to H0? Because that's the one that's used in shape analysis. Every active contour model that's called a gradient flow is a gradient flow only with respect to H0. So there was a lot of effort that was put in to try to fix H0. In particular, a couple years ago, I started some work with Andrea Minucci trying to use conformal factors on the metric, which would preserve the directionality of all the gradient flows. It would just change the way they're parameterized in time, in the hopes that you could come up with a good metric without having to change the way people do active contours. But although that fixed a lot of pathology, still at the end of the day, you couldn't even guarantee there are geodesics between points. It was certainly a lot better than H0, but it still didn't have all the properties you really want out of a metric. So what we've done is just said, okay, look, just forget H0. It's a bad metric. We're going to use something else. But if you're going to use something else, which people have been doing in shape analysis for a long time, it'd be nice if you revisited the problem of shape optimization and redid your gradient flow with respect to whatever new metric you're using for shape analysis. So what I'm going to propose now are Sobolev metrics. And what I want to talk about now for a few minutes before I show you the results is the intuition behind what a gradient is. Okay, so first I'll give you the actual definition of a gradient. This is the definition of a gradient, of an energy. If you give me an energy, and I know how to compute directional derivatives. So you give me a direction h, and I compute the directional derivative in h. So that's what the numerator is. Now I divide the directional derivative in h by the norm of h. So I have to put a norm on my set of directions. Okay, now of course if you give me an inner product in the set of directions, you automatically get a norm. The definition of the gradient is it's the supremum in h of this ratio. So I plug in all possible directions h. I take the ratio of the directional derivative divided by the cost of moving in that direction, and I choose the value of h that maxes this out for me. Okay. Now that's the definition. Now, in most normal spaces, certainly in finite dimensional spaces, with a decent Riemannian structure, you can interpret the gradient as follows. That instead of just looking at the direction and the cost of that direction, you actually take a small increment in that direction. Okay? And you look at the change of energy that you get by moving by that small increment divided by the cost of that small increment. Now the problem is if you have a pathological metric like the H0, the cost of any increment is 0. So you can't really have this interpretation. You need this definition up here. Okay. But if you don't have these weird pathologies, then in most cases you don't. You can think of it more intuitively as the direction that maximizes the ratio of the change in energy in that direction by how much it costs you to move in that direction. And now, of course, active contours are based on gradient descent, right? I'm trying to find the gradient direction for an energy, and I want to move in that direction or minus that direction. And what most work in active contours has done for the last few years to try to make the contour more and more robust to noise and less, less sensitive to structure, that could confuse it, is it focuses on changing. It presumes you're going to use gradient descent, so you're going to start with an energy. It focuses on changing just the numerator, and by changing the energy. So if your energy is really prone to getting stuck in local minima, it means throw that energy out, put in a new energy that's not as sensitive. Nobody has looked at modifying in the gradient descent algorithm the cost of moving the contour in any direction regardless of what the energy is. And that's what we're going to look at. So I'm going to propose now, so we need a norm that tells us how much it costs to move in any given direction. And we're not going to use the H0 norm anymore. So I'm going to propose now the Sobolev norm. So remember that the Sobolev consists of one component that looks like H0. I just take the magnitudes of any two vector fields on the curve, I multiply them pointwise, and I sum them up. Then in addition, I'm going to weight by some lambda this same type of integral, but where I'm going to replace the actual vector fields by their derivatives. And I'm going to sum them up. And then by choosing lambda, you can put more weight on the derivative part or on the zero order part. That's up to you. Okay, don't worry about this second version. I'm running out of time, so I'm just going to skip that. So what's nice about having this? So I'm taking the first order Sobolev case where I just take the zero order and then just one derivative. So this is my norm. So if I take some perturbation h and I look at the cost of that perturbation, it's exactly this. I'm going to sum up the actual magnitudes of each vector. I already do that in H0. But in addition, I'm going to sum up the magnitudes of the derivatives of the vector. So this is the new term right here. Now, why is this nice? So first, let's make sure we understand what this does for us. Suppose that these 2 points, v of s1 and v of s2, are two elements of a vector field on the curve. So I should call it h, but I'm calling it v. Okay, notice they're pointing in opposite directions. Now, if the cost of this is just from this first integral, so remember v is taking the role of h now. If all I care about is this term, then it doesn't matter that these two are pointing in those opposite directions. It just matters how long these two vectors are. And if I switch them so they point in the same direction, it's the same cost as if I leave them in opposite directions. This term, however, does not like these two things being in opposite directions. You pay a big price for this. If these are in the same direction, this is going to be much smaller. If they're in opposite directions, it becomes huge. Now, think about an active contour evolving in the presence of a bunch of noise and a bunch of fine-scale structure. What is it prone to do? If you've got a lot of fine-scale structure and noise that is giving you a very irregular force field on the curve, you don't necessarily pay a big cost for that in H0, as long as the magnitude of each one of those vectors is not too big. The fact that they're scattered in all kinds of different directions doesn't matter. But if you're using a Sobolev inner product, you pay a huge cost for that. Now, when you're computing the gradient, the cost that you pay for moving in a direction is very important, because it's the change in energy divided by the cost. Now, in the case of H0, if you've got a lot of noise, you get this really irregular vector field, but the change in the energy might be a lot more than if I took a smoother motion. And since it doesn't cost you to have this really irregular vector field, the gradient then favors this really irregular type of motion. However, if it costs you a lot to move like this, the gradient is going to be influenced by that. And now the gradient is going to prefer smoother motions of the curve because those cost less. So even if the change in the energy by moving in this weird scattered way is a little bit more than if you move in a slow way, the fact that the cost of moving in the scattered way is a heck of a lot more means that the ratio of the change of energy to the cost really favors you moving in a smooth way. So it's very unlikely with the Sobolev norm that the gradient of an energy is going to give you a really non-smooth motion. It's going to really try to move smoothly as much as possible. Now, how does that help you? It helps you avoid local minima, not because it gets rid of local minima. They're still there. It's the same exact energy. If I start with a contour being exactly at a local minima, the gradient will be 0 no matter whether it's with Sobolev, no matter whether it's H0, doesn't matter. Where it helps you is this. Suppose that your initial contour C is indicated by this green circle, which has a 7 in it. So each one of these circles represents a possible location of a contour. And then the values are the value of the energy. And I'm trying to minimize. So I want to reach this configuration here. This is the object that I'm trying to attract the contour towards. On the other hand, there's a whole bunch of local minima nearby the contours. So here's one that's 6 and 5. These are local minima. So the contour, if I move in by the gradient, is going to go to the closest minimum. And so I'm never going to reach this. Now, these minima that are really not nearby the contour happen all the time with most active contour energies in H0 if you have a lot of noise. No matter where you put the initial contour, if you have a lot of noise and a lot of texture, there's some weird configuration nearby that the contour wants to go to. And that's much closer than the nice object that you want to move the contour to. The trick of changing the metric without touching the energy is you still have all these local minima. But if your initial contour is smooth, and all these local minima are not smooth, then they're still there, but they get scattered. They look much further away now. And now this other boundary of the object, which has some of the same smoothness characteristics as your initial contour, it looks much closer to you. And now when you recompute the gradient, it's not that these guys went away. They're still there, but they've been pushed away. And now you go to a much better solution. So that's the trick. All right, now, just really quickly, how do you compute these Sobolev gradients? So the good news is that you don't have to go to every single active contour model in the literature that was proposed and redo a bunch of math to recompute the gradient. If you know the old gradient in H0, you can compute the Sobolev gradient by convolution. So you can show that the Sobolev gradient, that if I compute the H0 gradient of an energy, that the Sobolev gradient satisfies a certain ODE. And the solution of that ODE is obtained by convolving the old gradient flow that you know with a certain kernel. And this just shows what the kernel looks like. The kernel, of course, depends on what your lambda was. Lambda is how much weight you put on the derivative terms. The bigger you make lambda, the smoother this kernel is. The smaller you make it, the more. If you make lambda 0 to delta function, that means when you convolve it, you just get back the original H0. Okay, so you don't have to. You know, there's a straightforward way to take what you already know and implement it. So now this just shows the effect of it now. So here's a very noisy image. This is a region-based segmentation. I'm just trying to, it's just the Chen-Vézy energy that most of you know. And even though it's region-based, and region is much more robust to noise than edge-based, I've put so much noise in here that despite it being region-based, it still gets stuck in local minimum. All right, now what's the traditional way of fixing this? The traditional way is you change the energy. So you add regularization to the energy. Now it's a new energy. And now I've put a big penalty on the arc length of the curve. Now I start evolving, and now I get past the local minimum. On the other hand, the cost of that is that I've lost the corners. Because it's a new energy. I mean, so I'm going to get a new local minima. If instead you leave the energy alone, don't add the regularization in the energy. Start with the same exact initial curve. Now start computing the flow, the gradient flow with respect to the Sobolev metric. Notice that the curve evolves very smoothly in the beginning. That's because it's possible to make the energy smaller by smooth motions, and smooth motions cost less, so the ratio is very, very favorable. Here, the curve started to become non-smooth instantly because you could decrease the energy slightly more by this really irregular motion, and since the irregular motion cost the same as a smooth motion, it favored it. Notice that at the end of the day, you do get this noise effect. But it's only because by the time it's reached the boundary of this object, there's no more smooth motions left that reduce the energy. So the only way left to reduce the energy is by an expensive motion. But since there is no better choice, that's the one that wins. But before you reach that configuration, as long as there's a smoother motion to reduce the energy, the Sobolev prefers the smoother motion. So you're not constraining yourself to be smooth. You're not smooth. At the end of the day, you're not smooth. Okay? This did not come from regularizing the energy. This came from regularizing the energy by putting in the energy that you want to be smooth. But this is a much better local minimum than this one. And then this shows, let me skip this business in the Fourier analysis and just get to the last example. I'll show you another pathology with H0. So H0 has weird configurations of local minima, not just due to noise. If you take geodesic active contours, it's edge-based. Of course, we know these are very sensitive to noise, but here there's no noise. Suppose that you want to segment this, and you start with a contour here. If the contour has a lot of convexities, or concavities, you can get trapped into these weird local minima like this. If you think about it, the energy of this contour is less than if I move the contour over a little bit this way. Because what happens is, even though I pay a big cost for this part of the contour that's not on an edge, initially, if I move the contour a little bit this way, because this is a concave region, that means that initially the arc length of that piece that's not on an edge will have to get slightly bigger. And it will cost me more. So this is, in fact, a local minimum. But why did I get to this local minimum? Because every point on the curve really moved independently. So the points that were close to these edges, darn it, the points that were close to these edges moved down immediately. Okay, these points really didn't do anything because there was no edge nearby. So the only thing that really attracted them was kind of this second-order effective curvature. They move very slowly. In the Sobolev evolution, since the whole contour has to move in a very smooth way, there's a much global computation going on to tell you how the contour moves. So the cheapest thing for this contour to do is translate and maybe rescale itself because it's a very smooth motion. So it doesn't start immediately locking onto features. First it starts to stretch out this way and narrow in this way. And then it continues to do that, and it continues to, and then once it's exhausted these really smooth motions, then it starts responding by each piece of the contour individually, but only after it's first roughly gotten the overall outline of the shape. And as a result, you don't get trapped in this local minima. So even without noise, there's an advantage of doing the Sobolev. And then now I'll show you on a real image, and then I'll quit. So I'll do one edge-based and one region-based. So just two examples, and then I'm done. So here's the initial curve with a edge-based active contour, geodesic active contours, and I started very close to the edge, and because I started very close to the edge, I converged to a good local minimizer. Now here I'm starting just a little bit away from the edge, but not, in my mind, this is still pretty close to the edge, right? But as you see, you get stuck in this weird local minima. This piece here is stubborn. It doesn't want to go away. And the same thing about this piece over here. And again, it's because every little piece of the curve really moves independently. Because in the Sobolev, in the H0 gradient, in the norm, you just sum up the costs of each point, and you don't care how coordinated the points are. There's no derivative term. If instead, oh yeah. If instead you do the gradient now with respect to Sobolev, both of those same initial conditions converge to the same local minimum. And if you look at how it's evolving down here, notice that up here, each piece of the curve, this goes right to the edge, this goes right to the edge, this goes right to the edge. Notice what this curve is doing. First, it's kind of contracting. It's not changing its fine-scale structure much in the beginning. It's changing in very coarse ways. And then once it exhausts these coarse-scale motions, then it starts to fold in the fine-scale motions and then finally changes its shape. And by doing that, it skips over these little stubborn points where little pieces of the curve can lock onto it right away. That's not allowed here. And then just to show you that it works also in the region-based case, here's a comparison in the region-based case. So on the top, this is the Chanvese segmentation, but with very, very little penalty in arc length. There's very little regularization in this energy. And as you see, the answer that you get, each part of the curve moves independently. So this part of the curve down here starts to peel in, this part moves down, this part moves up, and then they break apart, and then you capture all these little tiny pieces of noise, and then of course you get this big mess at the end of the day. Okay, now again, standard way to fix this, add regularization to the energy, crank up the penalty, and force smoothness in the curve. All right, you do that, you certainly get a smoother curve, but still notice that up to the smoothness constraint, still each part of the curve moves rather independently. Again, you have these two pieces of the curve that are moving separately to kind of fill in the gap, and as a result, you get this topological change, and in addition to the thing you want, you get all this other garbage. It's smoother, but instead, take the same energy up here without the regularization. Run the Sobolev active contour. Notice the first thing that the contour does is it just translates. Because that's a cheap motion. The derivatives of translation along the curve are small. In fact, it's 0. Now, it rescales. That's a very cheap motion. It's a very coarse scale motion of the curve that costs you little under the Sobolev norm. Now, now it has no choice. The only way left to minimize the energy once it's got the coarse scale structure is now it starts to fold in the fine scale changes because that's all that's left. And so then finally it folds those in. But because it waited until the last minute to do that, you didn't have this pinch in effect here, so you didn't split. You didn't capture all these little pieces of noise along the way because they weren't allowed to split off right away. It's only at the very end that you capture some of the fine scale structure. And so you get a much better answer. All right, so and then I'll quit there. So I'm already over. So if there are any questions, go ahead.
Any questions?
Probably I missed it somewhere, but I know the energy form of the Yezzi and the geodesic, but what's the energy form of Sobolev?
That's the point. It's not based on the energy. So
Okay.
you give me a flow, you pick whatever energy you want, and the flow that you're going to take to minimize that energy is not going to be the one you used before. It's going to be a new one. So this is meant to plug into whatever your favorite energy is to squeeze out even better performance of the active contour.
Any other questions?
Yeah.
Question. So, is this new approach sensitive to the initialization for the active contour, or
Yes, because but it's designed to exploit a property that usually you have in the initialization. So the trick is that by changing the norm of perturbations, you change the path taken by the gradient descent. And you make some local minima that might have been close to you before look far away, and other local minima that might have looked far away before look closer to you. So, of course, this is crucial. Now the crucial question is, where are you to begin with, right? So the assumption that's being exploited by this is that your initial contour has most of the fine scale structure of the final contour. So as a result, it's more likely that coarse scale changes in your contour are going to get you to your result faster than fine scale changes. So if your object that you're trying to segment is smooth and your initial contour is smooth, then that means you don't need a lot of fine scale change to go from beginning to end. You can do it mostly with coarse scale change. On the other hand, if the object you're trying to segment is not smooth and your initial contour is very smooth, then it's going to look far away. Or vice versa. If your initial contour is really noisy and you're trying to segment a smooth object, it's going to take a lot of fine scale motion to undo the noise. And Sobolev doesn't like that. Okay, so the assumption that's being exploited here, which usually happens in most applications, is that you start off with a contour that has a lot of, it might not have the global characteristics, but if I look at a small piece of your curve, not knowing what the rest looks like, and I look at a small piece of the destination curve, and I just look at and I compare their characteristics at different scales, I'm assuming that they're more similar to each other than a random local minima due to noise. And so H0 doesn't exploit this at all, Sobolev does. So yeah, it does depend on initial conditions.
Any other questions? Now, if you went up on on a higher order, let's say for instance, you go up to the second derivative in the norm, Sobolev norm. So what would be the sort of the physical intuition behind that?
That's just paying even more cost for a non-smooth, for your perturbation. So,
No,
so
but I mean, I can see that in when I'm talking about the first order, then the rate, in a sense, the rate at which h varies, then but the second order, then I don't quite have physical interpretation for it.
well, usually the higher the derivative, the more strongly, the more sensitive it is to fluctuations, right? So if I just look at a first derivative and I have a really highly fluctuating h, then I get I get a certain penalty. If I go to higher derivatives, typically they get higher and higher and higher.
Okay, well, if there are no more questions, I guess we should thank our speaker.
There's actually, there's a more precise answer to your question if you look in the frequency domain. So suppose that you look at, you decompose